Okay, all right. So welcome back. I started recording. So last time on Thursday we came back to local fields, periodic fields, and we did unramified extensions in some detail. And today we will do non-unramified, ramified extensions. Okay, and we will see a nice application of Krasner's lemma towards the end. So let me start sharing the screen. So let me open the PDF file. Let me start sharing the screen. Can you confirm that you can see the slides?
Yes.
Yeah, fine. So let's start. Yeah. So today we will continue with periodic fields. And from next class onwards, we will come back to global fields. So I use this word local and global. Local meaning periodic fields and global meaning number fields, finite extensions of Q. Okay, so we will come back to global fields from next lecture onwards. Today we will finish chapter 2 of Lang. So we have studied unramified extensions, and now today we will study ramified extensions. So let's quickly recall what we did last time. Last time we discussed the finite unramified extensions of periodic fields. So remember, periodic field, the most important property, they are complete, and the ring of integers is a DVR. Okay, so then that gives a valuation, and with respect to that valuation, that absolute value, it's complete. And this is where you have Hensel's lemma and Krasner's lemma and all those things. So we discussed this last time. We proved that they are of the form K alpha. So you have a field K, and an unramified extension, finite unramified extension, is of the form K alpha. Where what kind of an element is alpha? It is such that it's minimal polynomial. Alpha satisfies a monic polynomial, which has a property, right? It's reduction mode P, so this has coefficients in O, and its reduction mode P will have all distinct roots, no multiple roots. So the reduction mode P has distinct roots. Then these are precisely the unramified extensions. And we saw that they are in bijection with finite separable extensions of the residue field. So what is this map? If you take an unramified extension, you take its ring of integers mod less than or equal to 1. It has a unique prime ideal, non-zero prime ideal, and you go to the corresponding residue field O by P. So that gives a bijection between unramified extensions of K and finite separable extensions of the residue field of K. This we saw last time. And when the residue field is finite, we proved at the very end, we proved this result that norm is surjective on units. The norm map, so if E over K is finite and ramified, you can take OE and OF, you can take the corresponding units OE star and OF star, and you have the norm map from E star to K star, and that is on units. It's surjective on units. And we also saw that a finite unramified extension is Galois. I don't think I gave a proof of this. Okay, we somehow assumed this and then went ahead and proved that it is actually cyclic, because what happens is once you know that it is Galois, you can consider the Galois group, and Galois group of E over K is isomorphic to the Galois group of the extension, residue field extension, which is a cyclic group. So this is cyclic. But why is it Galois? This also follows from one of the results that we proved, that it is given as K alpha, right? Where the minimal polynomial of alpha and its reduction mode P is the minimal polynomial of alpha bar. So what happens is, if you take F, in order to show that it's Galois, we are assuming extensions are always separable. Assume characteristic 0 if you want. And so in order to show that it's Galois, you have to show that it's normal. Minimal polynomial, it's a splitting field of its minimal polynomial. All the other roots are also there. And how does it follow? It follows because if you have f, the minimal polynomial of alpha, and you take f bar, and f bar is in the finite field, and in the finite field, you're assuming you are in the residue field is finite case. So it's in the finite field and it has all its roots there because that extension is Galois, you know that. So what you have shown is f bar splits linearly, and you have Hensel's lemma which will allow you to split f linearly. So f also has all its roots. So f splits linearly. So this is Hensel's second version. So from that it follows that it's Galois, and then we showed that it is cyclic because there's no kernel, right? Kernel is inertia, and inertia is trivial because it's unramified, right? Inertia is a group of order E, and E is 1. Inertia is trivial, and it is surjective from decomposition group to the Galois group of residue fields. That is surjective, but decomposition group is same as Galois group because there's only one prime. So it is cyclic. And today we are going to discuss ramified extensions. Okay, so let's start. So we have KOP pi as usual. O is a DVR, K is its quotient field. In that absolute value, K is assumed to be complete. P is a unique non-zero prime ideal of O, and pi is a generator of P, an element of valuation 1. Maybe I have used this word long back. It's called a uniformizing element, uniformizer, or uniformizing element. It's an element of valuation 1. Any other element of valuation 1 will be this times a unit. So fix 1. Let E be a finite extension of K, and then we have its ring of integers, its non-zero prime ideal, its uniformizing element, etc., which we will denote by subscript E. So recall that if you start with P downstairs, go up, then there is only one prime above, and there will be some ramification index E, and the residue field OE by PE is an extension of O by P, and this was the definition of F, and EF is the total degree. And we studied unramified extensions last time. This is same as saying E equal to 1. Now we are going to say E over K is totally ramified. So it's the other extreme. So you want to take a guess? What should be the definition? It's the other extreme of E equal to 1. In this identity, EF equal to E over K. So what is the other extreme?
E equal to the degree.
E equal to the degree. In other words, F equal to 1. So that's the other extreme. That is called totally ramified. Otherwise, in general, there may be some E and there may be some F. E equal to 1 is one extreme, that is unramified. F equal to 1 is the other extreme, that is ramified. That is totally ramified. And we say that an extension is tamely ramified. So I'm not saying it's totally ramified, tamely ramified if you have some E, ramification index, and that is not divisible by the characteristic of your residue field. Okay, so the characteristic of the residue field, let us say P, if that does not divide E, then you say that the extension is tamely ramified. So unramified is also tamely ramified in this definition. Okay, it could be ramified also, but then the residue, then the F is not divisible by, the E is not divisible by P, the characteristic of the residue field. Okay, so we are going to study totally ramified extensions and tamely ramified extensions today. So consider E over K, finite extension of p-adic fields. Consider all the unramified extensions of K contained inside E. So last time we saw, right? In towers, how does unramified behavior happens? If E over F is unramified, F over K is unramified, then E over K is unramified. If you have E1 and E2 unramified, then the compositum is unramified. So you consider all the unramified sub-extensions of E and let E subscript U for unramified, be the compositum of all those. What can you conclude about EU? This is a compositum of many unramified extensions. And if E1 and E2 are unramified, the compositum is unramified. So this you can apply many times, and EU is unramified. So we have seen last time that the compositum is unramified. Therefore, EU is unramified over K. What can you say about the extension E over EU? So EU is the maximal unramified sub-extension of E. So what can you say about E over EU? take a guess, and your guess will be most likely correct. Make a quick statement. You can be wrong, but you will be right, I'm sure.
Totally ramified.
It will be totally ramified because all the unramified thing is taken care of. The remaining is totally ramified. And how do you prove it? Do you already see a proof? Your guess is absolutely right. Do you see a proof? Suppose not, then there is a little bit of unramified thing coming above. Yeah, suppose not. So go by the definition. So you have F equal to 1, right? F equal to 1 means what? Residue field, there is no extension. So the residue field corresponding to E equal to the residue field corresponding to EU if it is totally ramified. And we want to conclude that that is the case. Suppose not. Suppose the residue field of E is strictly containing the residue field of EU. Then corresponding to that extension, you can lift and get an unramified extensions, right? Unramified extensions are in bijection with residue field extensions. So if the residue field of E is strictly bigger than the residue field of EU, corresponding to that, you can get an unramified extension of EU, but that's not possible because EU consists of all unramified extensions, the compositum of all those. So therefore, this is totally ramified. It has to be totally ramified. Otherwise, this residue field strictly contains this residue field, giving rise to an unramified extension, because that extension you can lift back and you will get an unramified extension of EU, which is not possible. So your guess is right, and this is the proof. Now, suppose E over K is totally ramified. We want to characterize, totally ramified and tamely ramified extensions. So if E over K is totally ramified, consider the minimal polynomial of pi E, the uniformizing element of OE. So this is a generator of PE. So consider the minimal polynomial. Its coefficients. So what can you say about the coefficients of the minimal polynomial? They will consist of conjugates of the element pi E, right? So for example, the last one will be product of conjugates, maybe raised to some power or something, but it involves product of conjugates. The second coefficient involves sum of conjugates, and the other coefficients will involve sums and products in various ways. Coefficients are always polynomial expressions in Galois conjugates of pi E, and therefore what can you say? So it will involve polynomial expressions in conjugates of pi E. So pi E is an algebraic integer. It belongs to the ring of integers. So its conjugates are also there. And you are taking products and sums. So they are all algebraic. On the other hand, these coefficients belong to the ground field. So they belong to PE because it involves pi E and various expressions in pi E. So they belong to PE. On the other hand, it belongs to the ground field. Coefficient because all conjugates are involved and you are taking various combinations, so they belong to the ground field. But what is PE intersection O? It is just P. So the coefficients are in P. All the coefficients of the minimal polynomial, they are in P. Because it's algebraic, you know that they are actually in O, that you know, but you have concluded that they are actually in P. Now I'm going to conclude something more about the constant term. So we know that all the coefficients are in P except the leading one. Leading one is 1. It's a monic polynomial. The leading one is 1, monic polynomial, and all the other coefficients are in P, we concluded. And I'm going to conclude something more about the last term, the constant coefficient. I'm going to say that the last term, constant term, is in P, of course, as we have seen, but I'm going to say that it's not in P square. Constant term, if you observe, it has absolute value. What can you say about the absolute value? It involves product of the Galois conjugates, but all the Galois conjugates have the same absolute value, right? This we have seen using uniqueness of extension. All the Galois conjugates have same absolute value. So you're taking product of all that. So product of all that, and all of them have the same absolute value, and therefore it will have absolute value, right? The product involves pi E, sigma of pi E, all that thing. All of them have the same absolute value, so it will be product absolute value of pi e power the degree of the minimal polynomial. So it is pi e power e, and where e is the degree of e over k. Why is e the degree of e over k? E is equal to the degree of e over k because you are assuming it's totally ramified. EF is the full degree and it is totally ramified. So because of this, and since Galois conjugates have the same absolute value. Okay. Yeah. So and therefore it follows that the constant term is in P, but it also follows, what can you conclude from this? Pi e power e is actually small pi. Not small pi, meaning the uniformizing element, the generator of small p. So you have also concluded that pi e power e has valuation 1 with respect to small p. In other words, it is not in p square. This we already know, it's in p, but not in p square. You agree with this? Because pi e power e is the constant term. I mean, it is the constant term has absolute value same as absolute value of pi e power e. So it is pi e power e times a unit. So it cannot be in p square, because if it is in p square, then you will have pi e power 2e. Because pi is pi e power e times a unit. So therefore, it's not in p square. What do you call a polynomial whose monic polynomial whose all terms are in a prime ideal and the last term is not in p square? What do you call such a polynomial? All the coefficients except the leading one, which is monic, they are all in p, and the last one is not in p square. If you know this much, then there's a name, no, for such polynomials.
It sounds like the Eisenstein criteria.
Yeah. Why sounds like it is exactly that, no?
No, but I don't know the name of the polynomial. I just know the criteria.
Okay. Yeah. So okay. So maybe that's not standard terminology. I call such polynomials Eisenstein polynomial. Yeah, it is Eisenstein's criteria. Sounds like yes. Yeah. In other words, the minimal polynomial of pi e is Eisenstein. So I don't know whether this is standard. Let's call it Eisenstein. Okay. This property. So minimal polynomial of pi e is Eisenstein. So what we have shown is if you have a totally ramified extension, if you take the generator of the prime ideal here, its minimal polynomial is an Eisenstein polynomial. Conversely, the same proof you can track back if you have an Eisenstein polynomial in OX. You can take any one of its roots and you show that that root generates a totally ramified extension. Same thing you can track back. Whatever we have discussed here goes back same way, and you can take an Eisenstein polynomial and any root of it, right? If you have an Eisenstein polynomial and if you take a root, then of course it's an irreducible polynomial because Eisenstein criterion, such polynomials are irreducible, and it will generate a totally ramified extension. So what you need to show is how does small pi ramify, pi in p, small p, how does it ramify? So you can show that it will be pi e power the degree that you can show using this. Yeah, basically the idea is here. So there's a small check, please do that. Yeah. So the conclusion of this slide is totally ramified extensions are characterized by roots of Eisenstein polynomials. So earlier we showed that saw that unramified extensions are characterized by polynomial whose reduction mode p has distinct roots. And now totally ramified extensions are characterized by Eisenstein polynomials. Okay, so here's a small exercise. Write down all the totally ramified cubic extensions of Q2. So you'll have to check what are the possible Eisenstein polynomials of degree 3 over Q2 that you can write down. Okay, try some exercise. And the question is, are they Galois? So earlier we saw that unramified extensions are always Galois. That follows from Hensel's lemma. Here it need not be, as you will see in this example. They need not be Galois. Okay, so let's do tamely ramified now. Let E be a, so I'm going to prove a small lemma first, and then we will classify tamely ramified extensions. So let E be a positive integer not divisible by P. What is P here? P is the characteristic of the residue field. So if characteristic of the residue field is 0, in number theory, for us the characteristic of residue field is going to be positive P. But even if it's 0, then everything is tamely ramified. Okay, so let's say generally, so P could be 0 also here, generally. So E be a positive integer not divisible by P, and let E be a finite totally ramified extension of K. I'm going to make a claim now. Let it be a totally ramified extension, and suppose pi naught is any irreducible element in P. So that essentially means it has valuation 1, right? Therefore, it's irreducible. And let beta be an element from the larger field E with this property that its absolute value. So sometimes I may not put this E because there's a unique extension. So in later slides, I will not put subscript E. It's understood. Absolute value is extended uniquely. And suppose you have a beta such that beta power E has the same absolute value as this pi naught. Okay. So pi naught is downstairs, beta is upstairs, and suppose beta power E is some number given which is not divisible by P. So this is the tame condition. Tame meaning P does not divide the ramification index. E is right now a number, it will turn out to be the ramification index. So suppose beta power E and pi naught have the same absolute value. Then we are going to claim that there exists a pi of order 1 meaning valuation 1 in P, such that one of the roots of this equation, x power E minus pi, is contained in K beta. Is the statement clear? What is given to you is one element of P, one irreducible element of P, and one element upstairs with the property that beta power E and this given element pi naught have the same absolute value, where E is some number which is not divisible by P, and then we claim that there is an element of order 1 in P such that x power E minus pi, if you consider this polynomial, this is an Eisenstein polynomial, and this polynomial has at least one root which is contained in K beta. So K beta is a field containing K and contained in E, and we are saying that at least the one root of this polynomial is contained in K beta. So this is, let's prove this first. But if you assume this claim, that x power E minus pi, if you take one of the roots belongs to K beta, then we can see that if you take the uniformizer, any totally and tamely ramified extension E of K is generated by a generator pi E of PE. Why is that? Because pi E has the property that pi E power E is pi times a unit. So that pi times a unit without loss of generality you can call pi. Okay, then pi E power E is pi. So by modifying this pi, you see that pi E power E equal to pi, meaning pi E is a root of this root of this extension, root of this polynomial. Now, if it is a root of this polynomial, because it is an Eisenstein polynomial, that will generate a totally ramified extension by what we have seen last time in the last slide. So pi E will generate a totally ramified extension, and it is tame of degree E, and it is tame because of the condition given on E. E is not divisible by P. Okay, so assuming the claim, any totally and tamely ramified extension is generated by a generator of PE. So let's prove this claim. So we start by writing beta power e as, so what is given to you is beta power e and pi naught have the same absolute value. Therefore, beta power e equal to pi naught times a unit. Where is this unit? Everything is happening in upstairs in E, in the field E. So U is a unit in OE star. Okay, this is what is given to us. But we also know that OE by P equal to O by P. Why is that? Because it is given to us that E over F is totally ramified. E over K is totally ramified. So because it's totally ramified, this we know, and therefore U is a unit. U is from here. So U is congruent to something downstairs modulo PE because of this equality. So we have a U naught in O star. It's in O, but it will turn out to be in O star such that U is U naught mod PE. Why is U naught in O star? Why is U naught a unit? Because if U naught is not a unit, then it will contain mod pi E, it will be 0. Therefore, U naught has to be a unit. If this condition is satisfied and if U is a unit, then U naught has to be a unit. So there is such a U naught. And now we are going to modify pi naught to pi by taking pi to be pi naught times U naught. So what I have done is, this is upstairs. This may not be downstairs, may not be in the ground field, but I modified this U by a U naught so that pi naught times U naught. Pi naught is from the ground field. It is in P. Now U naught is also in the ground field. Therefore, this element is in the ground field. So this pi is the pi that we will work with in the claim. See, we claim that there exists a pi of order 1 in P. That is the candidate pi, such that one of the roots of this is contained. So we are going to show that for that pi, one of the roots of x power e minus pi is contained in k beta. That's what we are going to claim. So now beta power e is pi naught times u, but u mod p is u naught, so it is pi naught u naught plus something in pe. So you can write it as pi naught u naught, which is pi, plus something in pe, but something in pe you can write it as u naught plus something in pe, but something in pe you can write as pi times x, where x is in pe. Okay, because you are replacing with u naught plus x, u naught plus x. So what you have is pi naught u naught plus pi naught x. Pi naught u naught is pi. So the remaining thing you get pi naught x. Let's say pi naught y, where y is in PE, but I adjust it by multiplying by u naught and u naught inverse, so you can take x to be in PE. Okay, pi x where x to be in PE. This is what you get. And the corollary to this is, if you take pi beta power e minus pi, what is its absolute value? What can you say? Because x is in PE, so what is the absolute value of x? Absolute value of x is strictly less than 1. And pi beta power e minus pi is pi x. Absolute value of x is strictly less than 1. Therefore, this is strictly less than absolute value of pi. Agree? This minus this is this, and the absolute value of this is strictly less than the absolute value of pi because x belongs to P. Absolute value of x is strictly less than 1. Okay? So keep this in mind, and to continue, consider this polynomial x power e minus pi. What is our aim? Our aim is to show that one of the roots of this is contained in k beta. At least one root of this polynomial is contained in k beta. That's what we want to show. So let's call this polynomial fx. Let us name its roots a1 etc. ae, roots in some algebraic closure. And we want to say that one of the roots is contained in k beta. So what is f of beta? F of beta is beta power e minus pi, and beta power e minus pi, since these are the roots, it is beta minus a1 times beta minus ae, and take absolute value everywhere. Okay. So this is the definition of roots. And let us note that mod ai power e. Take any I, take any 1, 2, 3. I is anything from 1 to e. And what is mod ai power e? Ai is a root, right? So ai power e is pi. So mod ai power e is mod pi, which is mod pi naught. Why? Because what is pi? Pi is pi naught times u naught. U naught is a unit. So mod pi is same as mod pi naught. So this is mod pi naught. And mod pi naught, what do you know? What is the starting hypothesis? Starting hypothesis is there is a pi naught and there is a beta such that mod beta power e is mod pi naught. So mod pi naught is mod beta power e. So you have this equal to mod beta power e. So what is the conclusion? Mod ai and mod beta raised to e, they have the same absolute value. Okay, mod ai and mod beta power e, same absolute value. And this is because f of ai is 0. And therefore mod ai is mod beta, because these are discrete, right? So discrete valuation. So mod ai equal to not discrete. I mean, you're just using that mod ai and mod beta positive, right? So a positive number power something equal to another positive number power the same thing. So these two numbers are equal. So mod ai equal to mod beta. And therefore, what can you conclude? Mod ai equal to mod beta, and remember this also, mod beta e minus pi is less than mod pi. We'll come back to that. So this you have for each I, this is true. For each I, this is true. Now what is f of beta? F of beta is beta power e minus pi. Beta power e minus pi. And what was the last slide? Beta power e minus pi is strictly less than mod pi. So this is strictly less than mod pi. Okay. On the other hand, so this you have strictly less than mod pi. So this is strictly less than mod pi. Beta power e minus pi is strictly less than mod pi. And what are we going to conclude from this? Yeah. So this is nothing but f of beta. So what you know is this product is strictly less than mod pi. This product is strictly less than mod pi. And from that you can conclude that mod beta minus ai is strictly less than mod ai for at least one I. Why is that? Because if for all I, if mod beta minus ai is bigger than or equal to mod ai, then you will get this is bigger than or equal to mod a1, next is bigger than or equal to mod a2, etc. So you will get the product is bigger than or equal to mod a1 times mod a2 times mod ae, but all of them are conjugates, they all have the same valuation, and that will be bigger than mod beta power if this is greater than or equal to mod ai, then the right hand side will be bigger than mod beta power e. What is the argument? If this was not the case, you will get the right hand side to be bigger than
Because the product.
which is mod beta power e. But if Yeah, bigger than mod beta power e. But what is mod beta power e? Mod beta power e is same as mod pi, right?
Why is the product mod beta power e?
Product is mod beta power e. Product is bigger than mod beta power e, but mod beta power e is same as mod pi, no? Because what is given to you is mod beta power e is mod pi naught, but pi naught is mod pi naught is mod pi. So this is mod pi, and you will get contradiction to this. You will get this is greater than or equal to mod pi. But you know that this is less than mod pi, therefore you conclude that at least for one I, mod beta minus ai is strictly less than mod ai. Agree?
Yes, sir.
So let us say that that I is 1 without loss of generality, call rearrange so that a1 has this property that beta minus a1 modulus is strictly less than mod a1. Okay. So this is without loss of generality. And also note that mod a1, so now we have fixed this a1. A1 has this property that mod beta minus a1 is strictly less than mod a1. Now mod a1 minus aj for any j, mod a1 minus aj is less than or equal to maximum of mod a1 and mod aj, and mod a1 and mod aj are same, they are all mod beta, so this is equal to mod a1. So this is true for all j. So you know that mod a1 minus aj is less than or equal to mod a1. So putting that here, what are you getting? Here you have mod beta minus a1 is strictly less than mod a1, and here we are saying uh, yeah, this is the other way inequality anyway. So let's continue. So this is clear. Mod a1 minus aj is less than or equal to mod a1, and therefore, yeah, therefore you consider f prime of a1, the formal derivative, right? F of a1 is f of x is x power e minus pi, and it has the roots a1 a2 etc, so that is x minus a1 times x minus a2 etc. So what will be f prime x? It will be x minus a2 x minus a3 dot 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 plus x minus a1 x minus a3 dot 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 etc. So when you plug in a1, all the x minus a1 things will cancel, so only x minus a2 up to x minus ae will remain, and you are putting a1, right? So it is the product of a1 minus a2, a1 minus a3 etc, and a1 minus a2, a1 minus a3, all these have absolute value less than or equal to mod a1, less than or equal to mod a1. Therefore this is, yeah, but here I'm not using that thing, I'm going to use that next time. This is directly from the formula for the polynomial. F prime x, fx is x power e minus pi, so f prime x is e x power e minus 1. Yeah, pi is a constant, so that goes. So e x power e minus 1, and you are plugging a1. So e times a1 power e minus 1, that absolute value, but that absolute value is same as mod a1 power e minus 1. Why is that? So this is same as saying mod e equal to 1. Why is mod e 1? Why is mod e 1? Go back to the hypothesis. Right? P doesn't divide E. So you have the periodic absolute value. So mod E is 1. E is a unit. Okay, so that you are using here for the first time. So from this mod E is 1. So this is mod A1 power E minus 1. On the other hand, this is same as A1 minus A2 etc. A1 minus AE, because all the AIs are the roots. So f prime A1 is on the other hand this equal to this. So what can you conclude? There are E minus 1 terms here, and the product is this, and on the other hand A1 minus AJ is less than or equal to mod A1. A1 minus AJ is less than or equal to mod A1. So this will be less than mod a1 power e minus 1, but it is equal to mod a1 power e minus 1. Therefore, the conclusion is this is an equality everywhere. Mod a1 minus aj equal to mod a1 for all j not equal to 1. Agree? So mod a1 minus aj is less than or equal to mod a1 obviously, but from this by sandwiching you conclude that mod a1 minus aj is equal to mod a1 for all j not equal to 1, and plug that in back here. You have got an a1 such that beta minus a1 modulus is strictly less than mod a1, but mod a1 equal to mod a1 equal to mod a1 minus aj for all j. Mod a1 equal to mod a1 minus aj for all j. Therefore, what you have got is mod beta minus a1 is less than, strictly less than, this is strict, less than mod a1, but mod a1 equal to mod a1 minus aj for all j. So for all j not equal to 1, you have got this strict inequality. What does this remind you of? ai's are the roots and beta is an element which is closer to a1 than all the other conjugates of a1. So beta is closer to a root.
So we did this in that kind of third lecture.
Yeah, so what was the name?
Krasner's lemma, I think.
Yeah, so this is Krasner's lemma. This is the hypothesis of the Krasner's lemma. And what is the conclusion of Krasner's lemma in this case? If there is an element which is closer to one root than all the other conjugates, then what do you conclude? You conclude that A1 is contained in K beta. So that was Krasner's lemma. So conclude that Ka1 is contained in K beta. So this is the crucial step. Krasner's lemma is applied. So this is what we have to prove, right? The claim is that at least one root is contained in K beta. So the proof is Krasner's lemma after doing some preliminary steps. So we claim that there exists a pi of order 1 such that one of the roots, at least one root of this polynomial is contained in K beta, and the proof is Krasner's lemma. So what we are doing is we are finding one root which satisfies the hypothesis of Krasner's lemma, and therefore by Krasner that root is contained in K beta. Okay. And therefore we have proved that any totally and tamely ramified extension is generated by a generator pi e of PE, because pi e satisfies this polynomial. This is Eisenstein. So you will get a tamely totally ramified extension of degree E, and E is not divisible by P, and therefore it is also tamely ramified. Okay. So this leads to a characterization of tamely ramified extensions. What we have proved is any totally and tamely ramified extension is generated by, you already know that a totally ramified extension is generated by a root of an Eisenstein polynomial. But if it is also tame, then that Eisenstein polynomial has a further property that all these middle terms are zero. It has only the first and last term. The Eisenstein polynomial has the property that it is of the form x power e minus pi when it is tame. Okay, so the crucial input here was Krasner's lemma, and this is what we have done. And conversely also we can say, so right now we have said, if you have a totally and tamely ramified extension, how does it look like? And conversely, suppose you have a root of x power e minus a, it's a polynomial in OX, any root, and we are going to say that it generates a tamely ramified extension, provided P doesn't divide E. Okay, so this is the crucial point. P doesn't divide the degree of this polynomial. This is crucial. That's where tameness is coming from. So any root of x power e minus a in OX where P doesn't divide E generates a tamely ramified extension of K. Let's do this. So write A to be A is an O, right? So it can be written as some power of the uniformizing element times a unit in O star, and let alpha be any root of this polynomial x power e minus a. and you want to show that any root generates a tamely ramified extension. So you have to show that k alpha over k round bracket alpha, the field generated by alpha over k alpha. So you want to show that k alpha over k is tamely ramified. So it's easy. What you do is you observe that k alpha is contained in this field. This is a field over k generated by zeta is an eth root of unity, a primitive eth root of unity. So you take a primitive eth root of unity, you take an eth root of u, and you take an eth root of pi, and adjoin all these to k, and my claim is k alpha is contained in that. Why is that? You want to show that alpha belongs to this field, but by definition alpha is a root. So alpha power e equal to a. Alpha power e equal to a. So alpha belongs to k a power 1 by e. But a power 1 by e is generated by pi power 1 by e, u power 1 by e, and a primitive root zeta. Okay. So k alpha is contained in this, where zeta is any primitive eth root of unity. No, not any. For a primitive eth root of unity zeta, k alpha will be contained in this. Because alpha power e is a, so you are extracting eth root of a and taking eth root of a, it will be contained in, you take eth roots of all these things and the root of unity. So k alpha is contained in this. So what do we need to show? Claim is that k alpha over k is tamely ramified. So k contained in k alpha contained in this. So what we are going to show is, yeah, it's enough to show. So we will check what is the ramification index of the total thing. The ramification index of this thing we will say is E, and P doesn't divide E is given to us. And this ramification index will divide this ramification index, because ramification index is multiplicative. So that will show that k alpha over k is tamely ramified. So that's what we have to do. So first observation is, if you take this much, this is unramified over k. Why is that? This extension is unramified because, see, adjoining zeta will lead to unramified extension, because x power e minus 1 modulo p, its reduction mode p, have all distinct roots. Similarly, x power e minus u, reduction mode p, has all distinct roots. So if reduction mode p has distinct roots, that characterizes unramified extension. So this is unramified. Reduction mode p of x power e minus b, where b is any unit, has distinct roots. Why does this have distinct roots? Why is the reduction mode p of this has distinct roots? It's not always true, but it is true because of this condition that p doesn't divide e, right? Therefore the reduction mode p has distinct roots. If e was p, then x power p minus b is same as x minus b power 1 by p whole power p. Then all the roots are same. Because p doesn't divide e, this has distinct roots, and therefore this is an unramified extension. Therefore this extension, this field over this field, is totally ramified. That anyway you know, because that is adjoining pi power 1 by e. So pi is, yeah, so the crucial point is, because this is unramified, pi is still a prime element in pf. In this field also pi is prime because it's unramified. So pi there would be the prime here, power something, but that power is 1. So pi remains a prime here because this is unramified. Okay, and because pi is a prime, if you adjoin pi power 1 by e, then this is totally ramified because this satisfies an Eisenstein polynomial. So this is totally ramified over f by the Eisenstein criterion, and it's also tamely ramified, as we know that p doesn't divide e. This will be totally ramified of degree e, and e is not divisible by p, therefore it is totally and tamely ramified. So we are done, because we have k is contained in k alpha contained in this, and what we just showed is that this part is has ramification index E. And therefore, the ramification index of this will be a divisor of that. And since E is not divisible by P, P cannot divide the ramification index of this. So K alpha over K is tamely ramified. Okay, so this is the reason. We can do a little bit more here. So this is what we wanted to prove. But suppose you also know that I have written alpha as pi power r times u, right? This coefficient A I have written as pi power r times u. And then I showed that if T doesn't divide E, any root will generate a tamely ramified extension. This we shown. And when is that extension totally ramified? That depends on this R. So if R and E are co-prime, so suppose in addition, so we have shown that it's tamely ramified K alpha over K. And suppose you also know that R and E are co-prime. In A, if you write A equal to pi power R times U, and suppose you know that R and E are co-prime, there should be a space here. Then you know that you can find S and T integers such that SC plus TR is 1, right? This is whatever, Euclidean algorithm or something. So you can do this. And now we are going to do a trick. Consider this element alpha power T. Alpha is this root. K alpha over K is tamely ramified. Now I am going to conclude that under this assumption, under this hypothesis, K alpha over K is totally ramified. So take alpha power T, pi power S, where S and T are here. Then what do you observe? Then you note that this beta power E and pi have the same absolute value. Why is that? Because beta power E will involve alpha power TE, pi power SC. So pi power SC, you remember, is coming here, and alpha power TE. But what is alpha power E? Alpha power E is pi, because alpha is the root of x power E minus pi. So alpha power E is pi, so it will be pi power T. No, alpha power E is not pi. The polynomial is x power E minus A. So alpha power E is A. So alpha power TE is A power T, which is pi power TR times a unit. So you are getting pi power TR from here and pi power SC from here, and pi power TR plus SC, that is 1. So therefore beta power E, by your construction of beta power E and pi have the same absolute value in K alpha. Therefore the ramification index of K alpha over K is bigger than or equal to E. Why is that? Because when you raise pi, you already have got an element of the same absolute value. So pi is beta power E times a unit. Now if this beta is irreducible, then the ramification index is E. If this beta is not irreducible, this beta will have, if this beta has valuation 2, then the ramification index is 2E. If beta has valuation 3, then the ramification index is 3E. So ramification index is at least E because of this construction. But on the other hand, the ramification index is always less than or equal to the degree. And what is the degree of K alpha over K? Alpha satisfies x power E minus A. So x power E minus A, it may be reducible, it may be irreducible, but in any case the minimal polynomial has to divide that. So minimal polynomial will have degree less than or equal to E. So from these two it follows that this is actually equal. So this is equal to this. So all these things are equal. So the ramification index is equal to, this is equal to this. It's an equality here because of greater than or equal to and less than or equal to. All these are equalities. Therefore, you have got an equality here. In other words, ramification index is equal to the degree. In other words, K alpha over K is totally ramified. So the claim is, if you have the polynomial x power E minus A where P doesn't divide E, then take any root alpha, then K alpha over K is always tamely ramified. And if you write A as pi power R U, and if R and E are co-prime, then in addition K alpha over K is also totally ramified. Okay. So we have got a good understanding of totally and tamely ramified extensions, and we had this unramified. We had these three results in towers. How do they behave? All these results are true for tamely ramified extensions. For example, if E is tamely ramified over F and F is tamely ramified over K, then E is tamely ramified over K. What is the proof? Because the ramification index of E over K is the ramification index of E over F into the ramification index of F over K. Because F over K is, let's say, E1 and E2, then the total ramification index is E1 times E2. If this is E2, because this is tamely ramified, P doesn't divide E2. If this is E1, because it's tamely ramified, P doesn't divide E1. So P doesn't divide E1, P doesn't divide E2, therefore P doesn't divide E1, E2. Therefore the total thing is tamely ramified. So that's obvious. So as the ramification is a multiplicative. Our second thing was this kind of a diagram. If E over K is tamely ramified and if K1 is any finite extension, then EK1 over K1 is tamely ramified. So in the unramified case, how did we prove this? E will be of the form K alpha, where alpha has some particular property. The minimal polynomial reduction mode P has distinct roots. So E is K alpha, therefore the composite term is K1 alpha. But conversely also it is true. So K1 alpha over K1 is unramified. That was the proof. Here also similar, because we have characterized tamely ramified. So because E over K is tamely ramified, E over K is tamely ramified, this will be generated by a root of x power e minus a. This will be generated by a root of x power e minus a. Okay, so if this is tamely ramified, let us say it is totally ramified over the maximal unramified extension of this. In that case, this will be generated by a root of x power e minus the prime element here, which is same as the prime element here. So this will be generated by a root of x power e minus pi over this, which is generated by some alpha unramified. So this will be generated by alpha comma a root of, let's say, beta, which is a root of x power e minus pi. So this is of the form k alpha comma beta. Therefore this compositum will be of the form k1 bracket alpha comma beta. But then, converse direction you can apply, it will follow that this is tamely ramified. So it's a corollary to what we have just done, that if this is tamely ramified and if this is any finite extension, then this is tamely ramified, this part, ek1 over k1. And as a corollary to both these together, if E1 and E2 are tamely ramified, then the compositum is tamely ramified. Why is that? Because if E1 and E2 are tamely ramified, because E1 over K is tamely ramified, E1 E2 over E2 will be tamely ramified. And because this is tamely ramified and this is tamely ramified, this will be tamely ramified by part 1. So the compositum of tamely ramified is tamely ramified exactly as compositum of unramified is unramified. Okay, and therefore we have this corollary. You consider E over K. This we did for unramified extensions, right? You considered all the unramified sub extensions and you took the compositum, and that we call E subscript U. That was the maximal unramified sub extension. Similarly, you can do for tamely ramified. You consider all the tamely ramified extensions of K inside E and let E subscript T, T for tame, be the compositum of all those. So from the last slide, it follows that ET is tamely ramified. Compositum of tamely ramified is tamely ramified. So ET over K is tamely ramified. ET is tamely ramified over K. What do you think about E over ET? E over EU is totally ramified. Therefore, E over ET also has to be totally ramified because ET contains EU. Right? Unramified is in particular tamely ramified. So EU is contained in ET. So E over ET is of course totally ramified, obvious. But we are going to say something more. We are going to say that E over ET is, this is the name in the title, wildly ramified. Wildly ramified. What does this mean? So wild is the other extreme of tame. Tame is, the English meaning of tame is domesticated or well behaved or whatever, right? Tame animal. Wild animal is something you can't domesticate. So it's the other extreme of tame. So what should be the definition of wild? Tamely ramified is P doesn't divide E. Tame is P doesn't divide E. If that is one extreme, what should be the other extreme? Take a guess and most likely you will be right.
P divide.
P divides C, but the other extreme. P divides C is just not tame, but wild is the other extreme. If P equal to, yeah, P need not be equal to E. E is a P power.
Yeah.
E is a P power. Okay, E is a power of P. So wild is E is a P power. But E is same as the degree of E over ET because this is totally ramified. So the degree of the extension is a P power or the ramification index is a P power. Ramification index equal to the degree. This is wild. And we are going to claim that E over ET is wildly ramified. So if you take all the tame part together, the rest is wild. Okay, so let's prove that. So to see this, write E as you take the maximum power of P outside and E naught where E naught is coprime to P. Okay, take beta to be the uniformizer in E raised to the power of P power R. So beta has the property that beta power E naught. So beta power E naught will be pi E power E, and pi E power E and pi have the same absolute value. That's the definition of the ramification index, right? E is the ramification index. So pi E power E and pi have the same absolute value is the definition of E. So by your construction, beta power E naught and pi have the same absolute value. So we have seen that one of the roots of x power E naught minus pi is in k beta. This is the lemma that we proved. This was Krasner's lemma, applying Krasner. This is the lemma that we proved using Krasner's lemma. So x power E naught minus pi, one of its roots is in k beta. So k beta contains, so let us say alpha is the root of this. Then k alpha over k is tamely ramified and k beta contains that extension. So the conclusion is k beta contains a tamely ramified subextension of ramification index E naught. Let's call it K1. Now it is easy to see that the compositum of K1 and the maximal unramified extension is the maximal tamely ramified extension. Why is that? Because you have already got a tamely ramified extension of ramification index E naught, that is K1. So if there is anything above this which is tame, if there is anything above this which is tame, either it is unramified, that cannot be true because unramified is contained inside this. If it is ramified, that ramification index has to divide E, but E naught is already taken care of in K1. So it has to be divisible by P, but then it's not tame. So the maximal tamely ramified subextension is K1 times EU, the compositum. Okay, and what is the degree of E over ET? Clearly E over ET degree is P power R, because the whole degree is P power R times E naught, and the degree of K1 over K is degree of K1 over K is E naught. Degree of K1 over K is E naught, and the totally ramified part will be E over K1. So E over K1 degree is E. E over K1 degree is E, and K1 over K degree is E naught. So E over ET will have degree P power R, because E over K1 will have ramification index P power R, and the degree of E over ET, see the rest is unramified. So this degree is P power R. So this follows from this factorization. So unramified, you take the composite term, and that's a maximal unramified extension, and anything above is totally ramified. Tamely ramified, if you take the composite term, you get the maximal tamely ramified. Of course, anything above is totally ramified, but not just total, it is wide, in the sense that ramification index is a prime power. Okay, so all these things have wonderful applications in number theory, advanced number theory, because you will get P groups, and P groups are important in group theory, right? So all those things can be used, but that's beyond what we can do, beyond the scope of our syllabus. Okay, let's finish today's lecture by proving a wonderful finiteness result. Okay, it is a beautiful application of Krasner's lemma. So let K be a periodic field, any periodic field. The question that we would like to ask is, how many totally ramified extensions can it have of a given degree? Okay, so we have already seen this, right? Totally ramified extensions are characterized by what? Characterized by Eisenstein polynomials. So by the Eisenstein criterion, any such extension of degree E is given by a root of an Eisenstein polynomial. So here AIs are in P, and U0 pi is in P, but this is not in P square. U0 is a unit. AI is in P and U0 is a unit. So this is in P but not in P square. So it's an Eisenstein polynomial. You take a root, so you take the distinct roots, and all the roots will give rise to totally ramified extensions. Two roots may give rise to the same, I don't know. So what you can say is number of totally ramified extensions of degree. This polynomial will give rise to totally ramified extensions less than or equal to E. So one Eisenstein polynomial of degree E gives rise to at most E many totally ramified extensions of K. This is something that we have already done. So now we ask, how many Eisenstein polynomials are there of degree E? I'm not interested in the number of Eisenstein. There may be so many. There may be infinitely many. I don't care. But I am interested in the roots of that, because it's the roots that will give rise to totally ramified extensions. So let's ask this question, and they correspond to, right? It's the coefficients that you are interested in. So they correspond to this tuple, AE minus 1, etc., A1 U0. And where is this tuple? This is in P cross P cross P, E minus 1 times O star. This is a unit in O star. So Eisenstein polynomials correspond to this thing, this particular thing. Assume that the characteristic is 0. Characteristic of your field is 0, so that any irreducible polynomial is, what can you say about an irreducible polynomial in characteristic 0? Yeah. What can you say if you are in characteristic 0? There's one important property of an irreducible polynomial. What can you say about its roots?
They are not repeated.
They are not repeated. In other words, the polynomial is separable. So any irreducible polynomial is separable. And we had a wonderful consequence of Krasner's lemma in lecture 2. I don't know whether you remember about roots of polynomials. Do you remember this? And at that time, maybe Manav asked me, but it's not effective. And I said, some part of number theory is to, try with examples. But even if it is not effective, it has a good application, and we will see it later, I told you. That's what we are doing now. Do you kind of vaguely remember what this consequence was?
I think we did something about reducible polynomial.
Yes, irreducible. And in order to do that, we said that.
Yeah, if some G is sufficiently close to F, then.
Correct. Absolutely. Yeah. So that is what we are going to use. So roots of polynomials close to each other. Polynomials close to each other. And this is the reference. So here there should be a pause. So this is a statement. I have cut and pasted the statement. If F is monic, irreducible, separable, and if G is monic of the same degree as F. I'm not saying G is irreducible. We concluded G is irreducible. I'm not saying G is separable, anything like that. It all can be concluded. So if F is monic irreducible separable, and if G is monic of the same degree, which is sufficiently close to F, we did not make it effective. Okay, sufficiently close to F, then roots of G have multiplicity 1. G is also separable. G is also irreducible. We are not interested in that here. Roots of G have multiplicity 1 and they belong to the distinct roots of F. What is sufficiently close? What is close? Close meaning mod F minus G is small enough. And what is mod F minus G? Mod F. We define mod F. Mod F is maximum of modulus of the coefficients. So in that distance, F and G are close if mod F minus G is small enough. How small? That comes in the proof. In the proof of this that came. And what is belong to? So you say that a root beta of G belongs to a root alpha of F if mod beta minus alpha is strictly less than the distance of alpha from any of its conjugates. Beta is closer to alpha than any other conjugate of alpha. This is exactly the hypothesis of Krasner's lemma. So we showed that roots of G have multiplicity 1 and belong to distinct roots of F. Given a root of F, there is a root of G belonging to that one. Distinct roots of G belong to distinct roots of F, and if a root beta of G belongs to a root alpha of F, this was a crucial thing. We showed that K alpha equal to K beta. This is what we showed as a consequence of Krasner's lemma. So the point is, if F and G are irreducible polynomials, if F is irreducible monic separable, we are going to apply it for an Eisenstein polynomial. So it is monic irreducible separable because we are in characteristic 0. Irreducibility implies separability. And if G is any other monic polynomial which is sufficiently close to F, then if you take any root of G and the corresponding totally ramified extension, if you take a root beta of G, the corresponding totally ramified extension is K beta. But this lemma is telling you K beta equal to K alpha. It's the same field. You're not getting another field where alpha is a root of the starting polynomial F. So what is the conclusion going back here? If you start with this F, and even if you have another G, but if G is close enough to this, the coefficients are close, G has coefficients BI's, but BE minus 1 is close to AE minus 1, BE minus 2 is close to AE minus 2, etc. Then this will give rise to some number of totally ramified extensions. And that polynomial G is not going to give you any new totally ramified extensions. All those are already obtained by this polynomial as a consequence of Krasner's lemma. In other words, if you have an Eisenstein polynomial corresponding to this tuple, and if you take a small enough neighborhood of this tuple inside this topological space, this is product topology. All these have topology coming from the metric, and this is a product topology. And if you take this point in this topological space, and if you take a small enough open neighborhood, how small? I don't know. We did not have an effective theorem. It doesn't matter. Small enough is enough for us. So if you take a small enough open neighborhood of this, and if you take the corresponding Eisenstein polynomial, I am not going to get new totally ramified extensions. Clear? So if you give me one Eisenstein polynomial, if you take the coefficient tuple, and if I take something from a small open neighborhood, some other tuple, and if I form the corresponding Eisenstein polynomial, I am not going to get new totally ramified extensions. So basically what we are saying is totally ramified extensions of degree E are bounded by this divided by an open neighborhood of this. Okay, so this divided by an open neighborhood of this. But what do you know about such a thing? So if you have this, and if you have an open neighborhood, and using that, if you cover this by translating, is that cover finite? you can always get a finite cover. If you take any open subset and using that, if you form a cover, you will get a finite subcover. Why? Because this is compact. Each of this is compact. Units is compact, P is compact, product in the product topology is compact. So because of compactness, compact by openness finite, so you are going to get, so the consequence for us is that a small open neighborhood of this point will determine the same extensions of K. So there are only finitely many totally ramified extensions of any given degree. This is because of topology, compact by openness finite. Okay, so conclusion is, if you give me a degree, there are only finitely many totally ramified extensions of that degree. And now we can conclude. Now let's also assume that K is a finite extension of p-adic numbers. Such a field is often called a p-adic field. Here you know my P is not the script P, it is a usual P. So when I say p-adic field with the usual P, not that Gothic P, that means it's a finite extension of QP. In this case, you know that the residue field is finite, and because unramified extensions are in bijection with residue fields, residue field extensions, you know that there is a unique unramified extension. So if K is a finite extension of QP, you can write it as a totally ramified extension over an unramified extension. And how many unramified extensions are there of a given degree? Exactly one, because it's a p-adic field, because it's a finite extension of QP. So there is an unramified extension, there's a unique unramified extension in any given degree, and that unramified extension may have some number of totally ramified extensions of a given degree. Both these put together, you conclude that the total number of finite extensions itself is finite. So for any n, it can only have finitely many extensions of degree less than or equal to n. Why? The proof is any extension is a totally ramified extension over an unramified extension, and for a p-adic field, there's a unique unramified extension of a given degree. So by Krasner, as we saw in the last slide, there are only finitely many totally ramified extensions. So this is a nice consequence. So even without effectiveness, we got a finiteness result. But what is that number? Their effectiveness of that result matters. We are only saying finite. So that is done. So one more pause here. And remember that this was the promised application of Krasner in page 14 of lecture 4. Okay, so we will stop here. And next lecture we will come back to yeah, let me stop sharing the screen. So next lecture we will come back to global fields, number fields. 9 students today. Okay. So let me also stop the recording.